So in talking about temperature, right, we think of it as hot or cold, of course, okay? But really what temperature is that it is dependent on the motion and the energy of molecules of a substance, right? Dependent on motion. I don't know why. I don't know what that word. I don't even think that's a real word right there. Emotional. That came from the textbook. I don't know what that even means. But kinetic energy, right? It depends on the kinetic energy of the molecules of a substance, right? Temperature is a measure of the average kinetic energy of the molecules of a substance, right? We always think of it as hot or cold, but you never think about it as being, the kinetic energy inside of it, right? And so, my laser died. There we go. What the heck, my laser? I was teaching chemical kinetics like 2 hours ago, and my students there are really, really hating me for that. So I think my laser is also hating me for that as well. It's very math heavy, a lot of calculus, differentials, and integrals. Aren't you guys happy you're not doing that here? Right? So, so a thermometer obviously is an instrument that utilizes the physical properties of materials, right, for the purposes of accurately determining the temperature. And then thermal expansion is the physical property that most commonly used to measure the temperature, right? And what we mean by thermal expansion is that, like a material, as it gets heated up, will expand, right? And in the case of a thermometer, if it's like a mercury thermometer, like old school style, there's a little bit of mercury inside of the bottom, and then it gets heated up, and that mercury expands, and that's how it goes up the thermometer. And you can use it to see what your temperature is, right? See if you have a fever that day. See if you have COVID, right? So, uh, expansion and contraction of a metal, right, which would be mercury, right here, or the newer thermometers actually have alcohol in them, red alcohol, right? Funny story about that is back when I was in school, I was in a class called organic chemistry, and we were doing lab, and one of the things we have uh, is this thing called a distillation apparatus that we use to distill alcohol, right? To make alcohol. And you have to put a thermometer at the top of it. Let's just pretend that this is a thermometer right here. And you've got to put a thermometer at the top of the apparatus, and there's a little stopper, and you put it through this little hole. So one of my friends, Danny, he got the wrong stopper with the little hole right there. And so it wouldn't go into the hole. And I'm thinking about it and laughing because I remember exactly what happened here. He he stuck it in there and he tried to squeeze the thermometer into the little rubber hole of that stopper. And I'm like, dude, I don't think that's gonna work, man. It looks like it's a little too small. He's like, no, no, man, it's fine. No, no, it's all good. And so he does it one more time real hard. It cracks and it breaks, and the thermometer slips out of the hole, goes straight through his hand, right? and and uh, and so the TA is at the front, and we're like, oh crap! We're actually cursing, but I can't curse in class anymore, so I'm not gonna do that. Anyway, they're like, oh crap, and whoever the TA was, and they run over, and literally Danny's like. It was I can't remember which hand it was. Maybe it was left hand. His left hand. Like waving his left hand, and there's a thermometer sticking out of it and blood coming down the side of it. Like it was crazy. It was absolutely crazy. So and the thing about it too is that it was a mercury thermometer, and mercury is actually very dangerous. So we had to call hazmat. They had to come clean up all the blood. They had to clean up all the mercury. And Danny came back the next day with his hand completely covered in bandages because he had the thermometer went straight through it. So be careful. I know you guys won't ever do that in here, but just be careful. Okay. So just to expand on thermal expansion, right? We have here a piece of metal. We have here we have here a piece of metal, right? I'm just going to use my finger now because my laser is dying on me. I don't have anything to point with. Anyway, so here we have a piece of long metal right here. At the top is iron, and the bottom is brass, right? And when you heat it up, right? When you heat it up, you can see that iron and brass actually have a different thermal expansion, right? They have a different thermal expansion. Brass actually expands more than iron, and that's why it's pushing upwards, right? If they had the same thermal expansion when they're heated up, they would just get longer, like straight out. But since brass has a higher thermal expansion, right? It bends more, it expands more. So let me ask you this question then: what if iron had the more thermal expansion? What would happen then? Which way would it bend? It would bend downward. Exactly. It would bend downward, right? So Um, yeah, that's really cool stuff right there. AC thermostats and dial type thermometers are based on bimetal coils. I didn't even know that. That's old school right there. I have a one of those EcoBees, digital thermometer kind of thing in my at my house. So it definitely has not got any metals in it. So a little bit more information here about thermometers, right? And you don't have to write all this stuff down. They're just facts about thermometers. The early thermometers, like, oh, here's this is actually a picture of a this is actually a picture of a analog mercury thermometer right there, right? And back in the day, they used two reference points to figure out what the lines of a thermometer would be, right? One reference point was the ice point, which is basically the temperature of a mixture of pure water and ice at normal temperature pressure, and another one's called the steam point, which is the temperature where there's pure water boils at normal atmospheric pressure, and that's how they figured out what the lines were going to be on a thermometer, right? Usually contains mercury or red alcohol. These days, though, everywhere you go, you see one of these, and they're shooting your forehead, right? See if you got COVID, right? Did to me at the movie theater the other day, right? And so these are infrared thermometers, and what they do is that they can shoot it right at your forehead and see what your temperature is on your forehead by reflecting the IR light from the thermometer to your head, and it comes back to the 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 IR thermometer and reads the temperature that way. So that's pretty cool. Um, what was I going to say? I forgot my. Oh, originally though, we never actually used these for testing people's temperature. See if they have a fever. Most of the time, if you worked in AC what is it called? HVAC, right? In the air conditioning, they use these thermometers to point up into the ceilings and to point out like ducts to see if your AC is working correctly. If it's putting out enough cold air, right? So we've actually already talked about this once before when we were talking about of the conversions of the temperature units, right? We have Celsius, Kelvin, and Fahrenheit, and I'm not going to make you do any conversions here, but I just want you to know that the steam points are where water boils, right? On a Celsius thermometer is 100 degrees Celsius. On a Kelvin thermometer, it's 373 degrees Celsius, and then on a Fahrenheit thermometer, it's 212 degrees Fahrenheit. I'm sorry, I should have said 373 Kelvin and then 212 degrees Fahrenheit, right? And then we're going to go down to the next one here, normal body temperature right here, right? Normal body temperature is 37 degrees and Celsius. 98.6 is for Fahrenheit, which you know that already if you've been taking your temperature, right? That's what they're trying to do when they see you've got COVID or fighting off any kind of infection, honestly, right? Room temperature is around 20 degrees, right? Or 68 degrees Fahrenheit right there. And then the ice point, which is the point that water starts to freeze, 0, 273, and 32, right? The other thing that's interesting here too is that the one I didn't talk about last time when we talked about this in the very first or second class was that there's another temperature that's important to know, and that's called absolute zero, right? Absolute zero is negative 273 degrees Celsius or negative 460 degrees Fahrenheit. But the important thing here, it's called absolute zero because in Kelvin scale, it's 0 degrees Kelvin, or sorry, 0 Kelvin, right? And what that means is, if you recall me talking about it before, when you look at anything that's made of matter, right, like a table or me or this wall or this board or water, my tea, for example, the molecules in that stuff are all vibrating, right? And we call that molecular motion. Okay, we call that molecular motion. It turns out that when you get down to absolute zero, there's no more molecular motion at all. It stops. All molecular motion stops, right? That's what absolute zero is. All molecular motion comes to a stop, right? Turns out that you can't ever get to absolute zero, but we'll talk about that later, okay? Your first question is an easy one. Which of the following units is a unit of temperature? Super easy one for the first one. I expect everyone to get this one right, but I won't speak too soon. I won't speak too soon. So far, everyone's gotten it right. Okay, that's 22 people. I think that's how many we have in here. And look at that. Everybody got it right. Good job. These are all units of temperature, right? All these. Celsius, Celsius, Fahrenheit, and Kelvin. Good job, guys. Good job. So this takes us to heat, just specifically talking about heat, right? So kinetic and potential energy exists at the molecular level too, right? We have the kinetics, which is the motion of molecules, which I was talking about how molecular motion is like things, the molecules inside this table are actually vibrating at a certain frequency, right? And then we have the potential, right, which is the compressing or the stretching of molecular bonds. And then the total kinetic and potential energies is called the internal energy, right? So heat is the energy that is transferred from one object to another as a result of a temperature difference, right? This heat energy is transmitted because of the temperature difference. So this was that thing I was talking about last time when, if you're like stuck in the cold, you don't have a heater, but you're with a friend, you should get naked and press up against each other, right? Because then you're going to transfer your heat much more effectively to your friend, right? Because remember how much heat do we put off as a human being? Exactly, as much as a 100-watt light bulb. I'm glad you remember that, right? So quite literally, if you were to, get naked with your friend, right, and hug up on each other while it's really cold, you can transfer 100 watts of heat back and forth, right, to keep each other warm. I have no idea. I guess it depends on the person, It depends on how big the person is, because the bigger the person, the more heat they have, the more mass, right? So honestly, I don't know. That's a good. Maybe that's an experiment we can do. Oh man. Okay, so the units of heat, right? The units of heats. The unit of heat is something that you heard of before, which is the joules, right? But most people call it calories, right? Most people call it calories. And so calories is the amount of heat energy necessary to raise 1 gram of pure water by 1 degree Celsius at normal temperature, right? So 1 calorie is equal to about 4.186 grams. I mean, joules, right? But the calorie that you're most familiar with here is the food calorie, the one that's on the back of nutrition, back of nutrition facts and stuff like that. I'm definitely keeping an eye on my calories, trying to lose weight for uh, my school portrait that's coming up soon, right? I haven't left. It was actually supposed to be last Monday, like 2 days ago, but I canceled it and rescheduled it because I hadn't lost enough weight yet, right? I've only lost Since I've been on my diet, I've only lost 7 pounds, and that's been no 9 pounds, 9 pounds. So it's been about a week, and I've lost 9 pounds. So hopefully by the end of the month, I've lost 40 pounds. So around there anyway, right? But anyway, so the food calorie is what you're most familiar with, and that is equal to 100 normal calories, right? 100 normal chemistry calories, and then that's also known as a kilocalorie, right? So basically, one food calorie is 4,186 joules. The British, though, they do something crazy called the BTU, the British Thermal Unit. And really, the only reason why I brought up the British thermal unit is because if you're ever in HVAC, doing air conditioning stuff, if you look at on every single AC unit there is, it says BTU on it, right? It says British Thermal Unit on it, which is basically the amount of power that kilowatt hours again, right? That that AC can do. So we talked about this a second ago about thermal expansion, right? With thermometers and stuff. And so, uh, in general, most matter, solids, liquids, and gases, they will expand with an increase in temperature and they will contract with a decrease in temperature, which makes sense because when you're heating something up, you're making the molecules spread more farther apart, right? And so when you drive over a bridge, like this bridge right here, you see these little gaps in the bridge right here, right? These little gaps right there. And those gaps are there so that when the metal expands, right, it doesn't crash into each other and break the bridge, right? Destroy the bridge. Interestingly enough, though, water is one exception to this rule. Water, when water actually freezes, right, or gets colder, it actually expands, right? And when it expands, it makes it so that it floats in water because it's less dense. Ice floats in water because it's less dense. And the reason why is because water is special. It actually It actually does the opposite of what most liquids, solids, and gases do. It expands when it gets colder. Crazy stuff, right? Why does water actually even do that? Well, taking a look at this graph here, right? We're very zoomed in right now on the density of water. And I've told you before that the density of water at like a normal temperature, say 4 degrees, is 1 degree Celsius. I mean 1 degree Celsius, sorry. 1 gram per mil, right? Right there, 1 gram per mil. But notice as the so this is the part that makes sense here, right? As the temperature decreases here, right? You're actually shrinking, right? And you're getting the water to become more and more dense. But then when it reaches that 4 degree mark and heads towards zero, it actually becomes less dense. It does the exact opposite of what most things do. And that's the reason why ice. That's the reason why ice floats in water, because it gets less dense when it freezes. The reason why it does that is because water has a special thing in it where, if you recall, water is made of one oxygen atom and two hydrogen atoms, right? And they do these cool things called hydrogen bonding. The hydrogens will actually bond, loosely associate themselves and attract themselves to the oxygen, right, of another water molecule. And when it does this, it actually makes shapes of hexagons, right? That's the easiest way it does it. It does it in shapes of hexagons, right? So if you get a whole bunch of water molecules together, right, and you start to freeze them, the hydrogen bonds in the water molecules will start make shapes of hexagons. And this is actually the reason why, when you take a really close look at a snowflake, right, the vast majority of snowflakes are what shape? Hexagons, right? They usually have 6 sides. I mean, you might find one crazy one someday somewhere, right? When this doesn't work out as well as it should. But the reason why snowflakes always have 6 sides, right? The reason why snowflakes always have 6 sides is because the hydrogen bonding inside of water molecules easily forms hydrogen bonds in the shape of a hexagon. It's crazy stuff, right? Have you ever looked at a snowflake that close before? Right? Well, I promise you, it'll be very cold this winter, and if we have another one of those freezes again, just get yourself a pile of snow and look at it under your like a magnifying glass, and you'll see that a snowflake, most of them, the vast majority of them, will have 6 sides. It's actually pretty cool. Okay. All right. Your next question: which of the following is an exception to the substances contract with a decrease in temperature rule? I'm gonna give up on my laser. Like seriously. Like I guess it just doesn't like math, and when I teach math, it gets very upset. Wow, you guys are on a roll today. You guys are doing great today. Oh, this is amazing. This is absolutely amazing. All right, everybody got that one right there. B is the answer because water is the only one that I mentioned to you today that is a exception to the substances contract with decrease in temperature rule, right? So I know that you will all get that question right on the exam, right? Because I've talked about it enough. Okay. So the next thing I want to talk about, the next thing I want to talk about is specific heat, right? So specific heat is the amount of energy or heat necessary to raise the temperature of 1 kilogram of substance 1 degree Celsius, right? And so the only reason why I brought this up here, right, is because I wanted to show you something very interesting. Okay. The units are this joule kilogram Celsius or kilocal kilogram Celsius, right? But just to put it another way, the greater the specific heat of a substance, the greater its capacity to store more heat energy. Okay. So have you ever used an oven, right, and had maybe a steel cookie sheet in there, right? And you bring it out, and it takes forever for it to cool down, right? But then, say you use the foil instead, use the foil pan instead, and you can just pick up the foil pan inside the oven and bring it out immediately. It doesn't get as hot, right, as the steel cookie sheet. Well, the reason why that is because when you look at this chart of specific heats, here's aluminum. And aluminum specific heat is only 0.22, right? Look at irons, right? Irons is less, right? And so that being said, the aluminum, right, is not going to have as much heat capacity as the iron's not going to have as much heat capacity as the aluminum, right? So actually, that doesn't make any sense because but that's just iron. I wish I had steel on here because steel is not just iron, right? Steel is actually a combination of many metals. So that doesn't work right. But just take my word for it because there's not a steel on this graph, right? Aluminum has a smaller specific heat than steel does, and that's why when you pull aluminum out of a fire, an oven, right, it's not as hot. But if you have a steel baking sheet in there and you pull it out, it stays hot and it's super hot. You don't want to touch it with your bare hands, right? So the other thing that has a lot of water, a lot of heat capacity is water, right? It takes a whole bunch of water. Sorry, it takes a whole bunch of heat to heat up water, right? And it keeps it for a very long time. That's why water can like stay hot for so long. Like your soup, you have to wait like 10 minutes before you can eat it, right? Because water holds on the thing for a very long time. But see, how many of you had a wooden spoon, right? If you have a wooden spoon in your hot water, it doesn't get very hot because its specific heat is only 0.4, right? So cool stuff, cool stuff. So there's an equation to figure out specific heat, which I'm not going to make you do it, but I just wanted to show you another thing that's super interesting, right? So the specific heat, which is H, right, is equal to the mass times the specific heat of the actual substance, right, times the change in water or change in temperature. Okay? So I'm going to ask you this question just in your head as a thought experiment, right? How much heat does it take to actually heat up a bathtub of 80 kilograms of water, right, from 12 degrees Celsius to 42 degrees Celsius? And 42 degrees Celsius is like normal bath temperature, right? Like kind of hot, but not super hot. You know, you can still get in the bathtub, right? All you have to do is plug all those things in, right, to the mass, the specific heat, and the temperature, and this is what you get. But does that mean anything to you? 2.4 times 3 times 10 to the third kilocalories? It doesn't mean anything to me until we take it and we convert the kilocalories to kilowatt hours, right? So for every kilocalorie, it equals 1.00116 kilowatt hours, right? So you can convert the kilocalories to kilowatt hours. And so to heat up your bathtub, right, it takes 2.8 kilowatt hours, right? And from when we were talking about last time, right? Right now, most people on electricity contracts with like Entergy or TXU, they're around 10 to 11 cents per hour, per kilowatt hour, right? It's not like those people on Griddy who have like, they're like 1 cent, but then when there's a free, they're up to like, a dollar per kilowatt hour, right? But since it costs 10 cents per kilowatt hour to heat up your bathtub, a normal bathtub, it literally costs you 28 cents each time you heat up a bathtub of water, right? So count up how many times you take a bath during a week, okay? And you fill up the bathtub, and it takes whatever. I don't know what yours is. Mine is 11 cents. Most people are around 11 to 12 cents, right? And then you can figure out exactly how much money it costs to heat up your bathtub. Isn't that crazy? I mean, don't you care about those kinds of things when you have high electricity bills? You know, I mean, I do. I thought it was a cool thing to do. It's kind of like that whole thing where you throw your bad boyfriend over the roof, and you can just all you need is gravity and his weight, and then you can figure out exactly how fast he was going when he hit the ground, right? And if they're a bad boyfriend like I am, you probably want it to be going pretty fast, right? So there's more energy in that. What happened here? I think I. Oh, I'm sorry. What happened here was I accidentally moved one slide before the other slide. Okay, so let's do this one first. Okay. So when we're talking about heat energy, right? When we're talking about heat and energy, we can talk about the phases of matter. Okay. Because, for example, water can be as solid as ice, right? And then when we melt the solid, it becomes a liquid. And then when we evaporate it to a gas, it's called vaporization. But then when we have gases, they can condense, right? They can condense to become liquids, and they can freeze to become solids. Okay, they can freeze to become solids. But gases can actually do this thing where they do deposition, right? Where it goes straight from gas to a solid without going through the middle one, which is liquid, or the solid can go straight into a gas, right? It can go straight into a gas, right? And you've seen this before. I know you have, and I'll tell you about it in a second. So that brings us to this slide right here. Sublimation is when a substance changes directly from solid to gas, right? And the biggest example here is CO2, frozen CO2 or dry ice, right? Have you ever gotten like a thing from Omaha Steakhouse before and it was shipped to you on dry ice and then you're like, oh, cool, dry ice. And then you leave it there for a day and then the next day it's completely gone. That's actually sublimation because the solid dry ice went straight to um, went straight to being liquid. I mean gas, right? Another good example too is that when you open your freezer, right, and you put something in your freezer and you leave it there for too long, what does it get on it? Freezer burn, right? But what is freezer burn? Freezer burn is actually literally is literally the liquid, right, inside your stuff, your uh no, sorry, the ice. The ice in your the ice in your frozen steak, for example, say you have a steak in there, you didn't seal it up very well, you just threw it in there, right? It freezes, but then what happens is that the ice that formed on your that formed on your steak actually goes straight into the gas phase, and that's called sublimation, right? And you're like wondering why your steak is so dry now after you've defrosted it, and it's so dry, and it's absolutely because it went through sublimation, right? It definitely didn't go through the liquid phase because it was frozen inside the freezer. It's too cold to go to liquid phase, right? So it went straight from solid to gas phase. Ooh, do people still use mothballs? I don't know about that. Oh, air fresheners. You know those little air fresheners that they put on the back of toilets. You open up the little cone. Those also sublimate, right? You're like, what happened to that stuff? Why didn't it turn to a liquid, right? Deposition is the exact opposite. It's when a substance changes directly from a gas to a solid, right? So that's like when you see ice crystals on your windows at winter, but it never rained, right? And it never rained. Make sense? Good stuff. So this is your next question. Which of the following phase changes skips the middle step of liquid? 'm gonna put that away before I hurt myself. I don't even know why that's here. Why is that even here? All right, let's see how well you were paying attention to that whole spiel. 14 people have responded. Wow, you guys are on a roll today. You just paying attention? Are the glazed eyes meaning that you're paying better attention than normal? Like, you know, I hear him though. I'm not watching, but I hear what he's saying. Because everybody, almost everybody, it was perfect for a while there. But almost everybody got that one right. The one that skips the middle stage is the sublimation. So good job there. Good job there. Whoever got that wrong, make sure you got that right next time on the test when I ask you about sublimation. Okay? So let's talk about pressure now. Pressure effects on the phase changes, right? When you increase pressures at lower altitudes, the boiling point increases, right? So a pressure cooker, what it does is that it makes high pressure inside of a little chamber here so that the temperature, right here, will the temperature for required to make the water boil actually is higher, and so you can cook food faster, right? So if you work at like KFC or you work at Chick-fil-A, what you're actually doing is you have oil in there, right? Some kind of fry oil in there, and they actually cook. I think KFC still does it. Maybe they don't anymore. I don't know, but I know for sure. I know for sure Chick-fil-A does it because I used to work at a Chick-fil-A, and they have pressure cookers just like the ones you would use at home, but instead of putting water in there to cook like to do like a roast, a pot roast or something, they put oil in there, and then they throw their chicken in there, their fried chicken in there, right? and they close it all up, and it takes like 30 seconds to cook the chicken nuggets from Chick-fil-A, or even the fried chicken from KFC, because it makes the liquid inside, whether it be oil or water, much hotter before it evaporates. Does that make sense? Right? Before it turns into a gas. I mean, think about it. Have you ever tried to fry chicken on your own before? Just like in a deep fryer on the frying pan? I mean, you could do it in 30 seconds, but you'll just get salmonella, right? But the reason why KFC brings out the chicken so fast is because they're using pressure cookers, right? They're using pressure cookers. Water boils at a lower temperature and must cook, so things must cook longer at higher altitudes, right? So you live in the mountains, it's the exact opposite because it's lower pressure, right? It's the exact opposite. And since it's lower pressure up there, the temperature is much lower before it boils, and so you got to cook things longer, right? Yeah, I wish I had a pressure cooker at home. It's probably super dangerous though. Probably super dangerous. And let me tell you, using pressure cookers actually makes your chicken juicier, right? Because nothing escapes the chamber, including the water, right? The juices of the chicken, right? And that's why like KFC chicken is so juicy, or even Chick-fil-A chicken is juicy as well, right? Right, yeah. So, well, see, and this is how you know it's like this too, because I don't know if you knew this, but Chick-fil-A, both Chick-fil-A and KFC, when they fry your chicken up, it's raw chicken that's covered in like, breading, and they fry it up, and somehow they get it done to you, and it's fully cooked, and you don't get salmonella, right? And that the reason why that is because they have pressure cookers. But when you go to McDonald's or something, their chicken nuggets that they give you, right? They're actually fully cooked before they even get to the McDonald's. And that's why they can just throw them into the regular old deep fryer without a pressure cooker, right? And they're fully cooked, right? So how do you get from a raw piece of chicken that can give you salmonella, right, fully cooked in like 30 seconds? The only way to do it is with a pressure cooker, right? The other restaurants like McDonald's give you chicken nuggets that are already cooked before they even get to the restaurant, and they just heat it back up again using I was about to say air fryer, but that's not what they have. They have deep fryers, right? It's crazy stuff. Okay, so whew, okay, sorry, I had to catch my breath there. So another interesting thing too is that in order for water to undergo a phase change from liquid to gas, the water molecules actually have to get enough heat for them to evaporate, right? And so that's actually the basis for why you sweat and why when you cool down when you sweat, right? Because literally on your body, if you're sweating, right, that water on your body, the sweat, has to evaporate. When it evaporates, it's the reason why it's even evaporating is because it's taking heat from your body to evaporate it. Well, it has to go somewhere. It goes into the water molecules, and the sweat dries and evaporates. And what happens to you? You cool down, right? That's how sweating works. I'm not really a sweater. I'm just kidding. I'm sweating right now, actually. But did you know that dogs don't sweat? I don't think dogs sweat. Someone told me that they sweat through their mouths. Yeah, that's a good call. Yeah, thanks, man. That's totally true. Anyway, so evaporations occur more quickly in dry climates and in humid climates, resulting more cooling in drier climates. So, and it makes sense too because if it's humid outside, you're always sweating. Nothing evaporates, right? But if you're in a drier climate, then you're evaporating very fast. Your sweat's evaporating very fast, and then so you get cooler faster. Okay. So let's talk about heat transfer then. There's a couple of different ways, or three different ways to do heat transfer. There is conduction right here, right, where you have like a metal object and it's conducting heat into your hand to burn your hand, right? And then there's convection, right, where it's going through like air, right here, hot air is touching your hands, right? And then there's radiation, which is just the light energy, the electromagnetic radiation, right, that's making you hot. So we'll go through each one of these individually. So conduction is heat transferred by molecular collisions, right? So literally the fire poker the guy had was getting hot, right? And it's getting hot because the fire poker is made of steel probably, and the molecules in steel are hitting each other harder, faster, and that's why it gets hotter. That's conduction, right? And so this is based on the thing called thermal conductivity. It's a measure of a substance's ability to conduct heat. One of our groups our houses in here did an experiment on conducting heat in their tea with spoons, but I don't know if they had tea. I think they just used water. It would have been better if they had tea, but that's okay. Um, but yeah, and they found that heat actually does conduct through spoons very, very effectively, right? Because when you put a spoon inside of a tea, a glass of tea when it's hot, it actually cools down the tea faster because of the thermal conductivity of the heat from the tea, right? Liquids and gases generally have very poor thermal conductors because their molecules are far apart, particularly gases. Some metals, though, since they're nice and solid, right, generally are really good conductors because their molecules are very close together, just like the metal spoons that one of our groups did in the lab. Then we have convection here, right? Here's a house, right, and here's a heating unit. Okay, here's a heating unit, and convection is literally pumping of hot air, right, through a house to heat it up. That's how we do heat transfer with convection, right? Another example of this is that is convection ovens, right? A lot of people like convection ovens a lot better than they like regular conventional ovens, like especially on like Great British Baking Show and on Nailed It and on what else? What's the other show I watch? MasterChef. They all have convection ovens, and the reason why they do that is because when you get the air circulating around like this, right, and it's not just sitting there, and it's circulating around like this, the heat transfer to the thing you're cooking is much better. It's much more even, so you get more even cooking. Things cook faster, right? I actually have a convection toaster oven in my office right now too. That way I can heat up my frozen pizza, right before class and eat it before I come here, right? So convection ovens are awesome. But the thing to remember, though, is that convection is the movement, right, of, oopsies, convection here is the movement of heated air, right? But whereas conduction is the transfer by molecular collisions, okay? So the third type is radiation, right? And that is this transfer of heat energy or energy itself using electromagnetic waves. The sun is the best at that, right? The sun is the best at that. And you know how you can just stand out there and be in the sun and it warms you up, right? And that's radiation right there, right? There's no there's no conductor, there's no spoon connecting you to the sun, right? And so there's no conduction there, right? You're definitely not getting any hot air from the sun, right? So you're not getting any convection from the sun, but what you are getting is radiation from the sun. Okay? So be able in the next task to differentiate between convection, conduction, and radiation. And if you can't, if it's hard for you to figure like to remember, just think about it in the way that you would use in your own house, right? Just think about it in the ways that you would use it in your own house. So, next question. What type of heat transfer involves the movement of heated air? Well, we're doing great on time, guys. I always feel like I'm behind in my other classes, but you guys keep me on track. It's great stuff. Keep me on track. All right, so far so good. So far everybody's getting it right. I've got 16 responses so far. 17, 18, 19, 20, 21. Okay, there we go. That's enough. All right, so again, the vast majority of people got this one correct. The answer here is convection, right? You guys are just playing with me, right? This is a joke. That's why not everybody got that one right, right? Okay, so it's just you punking me. And is that what it is? Am I being punked right now? That's a show that you probably have no idea what I'm talking about, do you? Punked. Anybody ever heard that show before? It's on. It was on MTV. It had Ashton Kutcher on it. He like punked celebrities by playing jokes on them and stuff. Like that one time he pretended to be like a tax officer and like confiscated all of Justin Timberlake's possessions. And Justin Timberlake was like crying. It was great times, you know. So now in my generation, not your generation, and we're not even that different in age, but in my generation, when someone's like playing a joke on you, you're like, "Are you punking me?" Right? So, but anyway, that's what that is, right? I mean, you guys all knew what the answer was, right? Just tell me you did. Just lie to me. Okay. Convection is the answer here. Convection is the answer. Okay, so let's talk about insulation then, right? So how does insulation work then? Well, insulation works because when you look at something like insulation, right, for a house, for example, right, there's a lot of gaps in it, and it's got a lot of like air. And air is a very bad conductor of heat because the gas molecules are so spread out, right? And heat has to travel this path, right, to actually get things heated. And so, since the gas molecules are so far apart, it makes it very slow. Heat can't travel through insulation very well. Whereas on the other hand, if you have something metallic, right, you have something metallic, those molecules are so close together, heat travels through that super fast. Okay, so we take advantage of that property using insulation because with insulation there's so much gaps and air in there, right? That it does a good job of keeping heat in or heat out, or vice versa, the cold in or cold out, right? And so another example would be like sleeping bags too, are like that as well. Pot holders are like that too. Oh, everybody's making the switch right now to double pane windows, right? Double pane windows because there's a little tiny gap inside with the windows, and so if there's air there, the heat doesn't pass through as bad, right? I'm making the switch. Wait, maybe my house already has double pane windows. I don't know. If it doesn't, I'm making the switch. Dagnammit. So there's a very special kind of insulator, right? And it's called a vacuum, right? And we all have one. Everybody in here, not everybody in here has one, but if you have one of these like um, Yetis, these Yeti tumblers right here, right? This is a Yeti tumbler that got completely decorated by my girlfriend, right? Which is amazing because I'm a bad boyfriend. So thank you for her. You're making me this thing. Anyway, when you look at this tumbler right here, it's actually very thick, and the reason why it's very thick is because there's two walls. There's the inner wall and there's the outer wall. Okay, and then inside of the inner wall is this space here, right? And most people think it's just full of air, but it's not. It's actually a vacuum, right? So think about it like this. If gases make it very difficult for heat to transfer because the molecules are so spread apart, right? Then in a vacuum, that's the best insulator, isn't it? Because there's no molecules there for the heat to transfer. Does that make sense? Right? And that's why thermoses work so well. That's why a thermos can keep your soup hot the entire day. Because there's no heat transfer when there's a vacuum, right? There's no heat transfer when there's a vacuum, right? So if I ask you a question like, what's the best insulator? What are you going to say? A vacuum, right? A vacuum. So taking a look at this on a chart right here, right? Notice how copper has really good heat conductivity. That's the reason why wires are made of copper, right? That's the reason why elements in your heating elements for like different types of heat, like hot plates and heating things, right? Those are all made of copper. Iron's also a very good heat conductor, right? Brick, not that good, right? So that's why a lot of houses are made of brick too, not just because it's strong, because it can be a little bit of insulating, right? But you jump all the way down here, and look at this. Cotton is a good insulator, not a very good conductor. Styrofoam is really good. That's why when you get styrofoam cups, has anyone noticed how every single fast food restaurant is out of styrofoam cups? Is that just me, or is that actually really happening? Like yeah, because I went to Buc-ee's the other day and I wanted like one of the really big Bucky cups, right, of like iced tea, and they were like, "Sorry, we're out of those cups." Like, what? How's that even possible? How could Buc-ee's be out of styrofoam cups? That's crazy. But the problem though is styrofoam is so cheap and it's such a great insulator. Oh, we're screwed. All of our drinks are going to melt. Ice is going to melt in our drinks. Going to water them down, just because we have no more styrofoam. This is a crisis. This is an absolute crisis when there's no more styrofoam, right? And then everybody knows why styrofoam is such a great insulator, though, right? It's because it's mostly made of air, right? Mostly made of air. And then air, of course, very low. But of course, the one that has no heat conduction at all is what? A vacuum, right? Good stuff. So continuing on with the phases of matter, right? We have three phases of matter, which I've talked about already before. But just to reiterate here, we have solids, liquids, and gas. Those are the common three phases of matter, right? And so the pressure and temperature determine which phase of the substance exists. So at normal temperature and pressure, copper is a solid, for example, right? Water is a liquid, for example, at normal temperature and pressure, right? By the way, here at normal temperature and pressure, we're at 1 atm as pressure, and temperature is like whatever the thermostat says. I think it says 68 degrees, something like that, right? And then oxygen is a gas, right? Oxygen is gas. So let's take a quick look here at solids, right? Solids are very close. The molecules are super close to each other, right? And when they're this close to each other, they do this thing that we call this a crystalline solid, right? And it makes a repeating pattern that's called a lattice, right? It's called a lattice. Okay. Upon heating, though, they vibrate more, right? And they vibrate so much that as you heat it up, it starts to expand, right? And that's why metals expand. Metals and other solids expand when you heat it up. Okay. There is things called like amorphous solids, right? Like glass, they lack ordered molecular structure. You don't have to worry about that. The vast majority of it, though, will have this crystalline solid, and when you heat it up, and they spread out. Okay. So liquids, though, they may move and assume the shape of any container, right? Liquids have little or no lattice arrangement, and liquids have a definite volume, but no definite shape. So generally what we say about liquids is that liquids will take the shape of the bottom of its container. See, like that. Okay, so so liquids expand when they're heated, of course, right? And then if you heat them up too much, they'll just boil. They'll just evaporate. They'll just evaporate. Moving to gas, though, gases are completely different from all of them, right? Gases, gases when they reach the gas phase are completely free from each other, right? They actually assume the entire shape of the object in the entire container. The pressure, volume, and temperature of gases are closely related. They're closely related in gases, right? Closely related. So just so that we can know for a fact for sure the difference between the three phases, the uh, solids always have a definite shape and volume. Okay, solids have a definite shape and volume. Liquids have definite volume but no definite shape, right? But gases here, right, don't have. They actually just no definite thing at all. They just take the shape and size of their container. Okay, so that's the difference between the three phases of matter. But then we have a fourth phase of matter. The fourth phase of matter is called plasma, right? And plasma is really just a gas that's been electrified, right? And you've seen plasma before. Plasma is like the stuff that's in like neon bulbs, right? Or has anyone ever seen those things called plasma balls, where you touch them and then like the electricity sparks up and touches your finger? That's plasma as well. Those are all plasma. Okay, so it really is just electrified gas. Okay, plasma, an extremely hot gas of electrically charged particles. Good stuff. That's a fourth phase of matter now. So here we go. Which phase of matter has a definite shape and volume? I have faith in you. I have faith in all of you to get this one correct. Which phase of matter has a definite shape and volume? About 18 responses, 19 responses, 20. All right. Again, the vast majority of you got that correct. The ones that didn't get that correct, make sure you get it correct so you can get it right on the exam. A solid is the only phase of matter that has a definite shape and volume. Okay? So there's this thing called the kinetic theory of gases, right? And really all it says is that gases consist of molecules that are moving independently of each other in all directions in straight lines, right? At high speeds. Okay? The higher the temperature, the higher the average of the speed of the molecules, which makes sense, right? We've been saying that already before. And then gas molecules collide with each other in the walls of a container. And when so gas molecules collide with each other in the walls of a container, this is what causes pressure. Okay? This is what causes pressure. The distance between molecules is on average large when compared to the size of the molecule. It's very large. So what that means is that when you look at a gas and you look at the molecules of a gas, there's a bunch of space between each molecule of gas. Okay? Bunch of space. So that brings us to these conclusions right here, right? The result of the collisions of billions of gas molecules on the wall container, a balloon, for example, or a ball, right? The more gas, the more collisions. The more collisions, the more force on the container, and then that means what? More pressure. The higher the pressure. Okay? The higher the pressure. So let's talk about pressure real quick, and don't worry about so much math here. I don't really care about all the math, right? But pressure is, we were talking about force before, pressure, little p here, right? Little p pressure here equals the force divided by the surface area, right? And so notice it's a big A. It's not a little a. What's little a? Exactly, acceleration, right? And so the point of this slide is just to tell you, right, is that as the A decreases, the surface area decreases, the pressure increases, right? And that's the reason why when you put a like a push pin into your finger, you can make it like really make it like puncture and make you bleed, right? Because when you have a smaller surface area, the pressure is much higher, right? And that's why it can puncture your skin. But if you were to have 10 of those there trying to go through your skin, it wouldn't because the pressure is spread out a bigger surface area. Does that make sense? Right? That's the reason why some of these crazy people can go lay down on a bed of nails, right? Because when they lay down on a bed of nails, it's a lot of surface area and not that much pressure. But if that guy went and laid down on one single nail, right, like that guy on Home Alone when he stepped on the nail, right? Like that guy, Marv, I think his was Marv. Yes, Marv, that's his name. He stepped on that nail, right? It was a single. I bet you if he had stepped on 10 nails, it'd been fine. But since he stepped only on one nail, he had a very bad time of it, right? Very bad time. Okay? Very bad time of it, right? So there's some relationships that we can think of here, right? And these are the kind of questions I'll be asking you on the exam. There won't be any numbers, right? But they're going to be about relationships, okay? So if we hold temperature and volume the same or hold it constant, the pressure is directly proportional to the number of gas molecules, right? So here we can see the temperature is 27. Here the temperature is 27. Both volumes of the container, right, are the same. But in this one, there's less gas molecules than there are in this one, right? And since there's more gas molecules here, there's more collisions, which means that what? The pressure is higher, right? Does that make sense? Okay. So, but this time, let's say we hold constant the volume and the number of gas molecules. Okay. And this time we change the temperature. So here you see the volume is the same. The number of gas molecules is the same in both, right? But on this side, we have a burner here heating things up, right? And since we're heating things up here, it's already up to 327 degrees. Holy mother, that's hot, right? And then the pressure increases, right? So as temperature goes up, what else goes up? Pressure, right? Makes sense? Then let's say we hold the number of molecules and the temperature the same, but this time we change the volume, right? So here's the number of molecules is the same as this, right? The temperature are both 27 degrees, but then now we made the volume smaller. What happens? The pressure goes up, right? So when pressure goes down, well, sorry, not pressure. When volume goes down, what happens? Pressure goes up, right? So I will ask you questions like that on the exam. I will say things like, if you hold this and this constant and you heat it up, what will happen to the pressure, right? Or whatever. Does that make sense? I care more about the relationships than I do about the numbers. Okay, so that's what I'm going to be asking you about. So here's your next question. Which of the following causes more pressure? More gas molecules, more collisions, more force on the container, or all of the above? Oh, so far you're doing great. So far you're doing great. Wow, so far it's wonderful. 16 responses so far. 17. Dang, we have one person did it wrong. Okay, we only have 19 responses, but okay, let's just keep moving right here. So yes, all three of these right here, all three of these are going to contribute to more pressure. So all of these are true. All of these are true. Okay, all those are true. So let's quickly talk about the laws of thermodynamics. Okay, I know it says a lot of stuff here, but the thing I want you to know about the law of first law of thermodynamics is this last line right here. Okay, the first law of thermodynamics says that energy can never be created or destroyed. Okay, all that stuff up here comes down to this: energy can never be created nor destroyed. Okay, and the example here is what we have here is called a heat engine. Okay, so there are many things that can be heat engines, right? Car engines are heat engines, right? Refrigerators are heat engines too, except in reverse. Guns are also heat engines as well, right? Um, so what happens is that in a heat engine, right, you'll have a high temperature reservoir or something that's super hot, okay? That's super hot. And some of it actually goes out to do some work, right? But the rest of it goes somewhere else, right? To just kind of dissipate, to cool down, right? And so when you talk about, for example, a gun, right? When you fire a gun, the huge explosion that happens with a bullet exits the barrel, right? That's the high temperature reservoir right there, right? That's the explosion, right? And some of that heat and that explosion is making the bullet fly out of the barrel, right? Where's the rest of the heat go? Quite literally, it goes into the gun, right? That's why guns get so hot when you shoot them. Does that make sense? Right? Guns get really hot when you shoot them, right? So, for example, like uh, when you're shooting like a machine gun, like in shooting like a machine gun, like on a tank or something like that, like they're fully automatic, so they're like shooting really fast and they don't stop for like a long time. They get so hot that they overheat, right? And when they overheat, the barrels aren't shooting straight anymore, right? And you'll see all this like smoke. And sometimes they'll have to, cool it down before you shoot it again. And sometimes you can pee on it to make it cooler, right? And then you can start shooting it again. Okay. Same thing with the car. The car engines are the same thing too, right? You have this huge explosion of gasoline that makes the car run, but that's only some of it. What happens to the rest of the heat? It goes into making the engine super hot, right? That's why you pop the hood of the car. You should never touch the engine after you've just turned it on, because the heat of the engine, right, is super hot. So some of it went to turning the wheels of your vehicle, but most of it went to where? Making your engine hot, right? And that's why you have to have radiators and cool your engine down. If your engine overheats, it doesn't work anymore, that kind of thing. But be clear though, the first law of thermodynamics says this: energy can never be created or destroyed. And so in that example, right, some of the energy went into pushing out a bullet out of a gun, but the rest of it went to where? It went to heating up a gun and made the gun really hot, or a car. Then we have the second law of thermodynamics, right? And what the second law of thermodynamics says is that it is impossible for heat to flow spontaneously from a colder body to a hotter body, right? From a colder body to a hotter body, right? So imagine, right, that these two blocks right here are two naked people, okay, and they're trying to keep warm, okay, right? Two naked people, they're trying to keep warm, so they're touching each other now. They're hugging on each other naked so they can try to keep warm, right? Spontaneously means that it's just going to happen. What's going to happen is that the heat from the warmer person is going to go to the colder person, right? Until you get to a point where both people hugging each other are the same temperature, right? But the interesting thing about it is that it's a bad deal for the person who's like got the heat because now you're colder than you were before, and the person you're trying to warm up is warmer. So hey, great, you helped your friend out, but you yourself are like cold now, colder, 5 degrees colder, right? So, but what the second law of thermodynamics is that the colder person can never transfer heat to you, right? So really, it's like it's like a give, it's a give take kind of relationship, right? It's not a give give, it's definitely a give take, right? Unless you both are like the exact same weight, right, and the exact same shape, you know. So I guess the only time it's actually fair is it's if it's your twin, right? And then we have the third law of thermodynamics here, right? And the third law of thermodynamics here says that it is impossible to attain a temperature of absolute zero, which I alluded to this before. I talked about this a second ago, right? Absolute zero is the point where you have no molecular motion at all, right? But the reason why you can't get ever to absolute zero is because there's always a path for the heat to follow, right? So here it's like what's happening with like a refrigerator, okay? And so the refrigerator is pumping in, right, cold to make the hot cooler, right? But there's always a way for the hot side to get more heat somehow, right? So this is like an AC or a refrigerator, right? And since there's always a way for the heat to get in there, you can never get to absolute zero. Okay. Um, I forgot to say something, didn't I? I think I forgot to say something. I forgot to mention something. That's okay. Let's just skip this question because I forgot to mention that. All right. So now we're going to go in the last 10 minutes or so, talk about waves and sound. And this is really, really easy. Okay. So we have waves. Okay. We have waves. And the thing about waves is that um, this, for example, these are waves in water, right? And they generally go up and down, right? Have you ever seen a wave in water go sideways? Like, does it go this way? No, it usually goes up and down, above, up and down, right? And but the funny thing about it is that like when you have like an earthquake, the waves go all different directions, right? So in a liquid water, like water, waves actually go up and down and not sideways. But in an earthquake or a solid, waves go sideways in all which directions, right? Sound waves travel through the air, and electromagnetic radiation travels through space, right? So we know that when matter is disturbed, energy emanates from the disturbance, right? And the propagation of that energy is known as a wave. Okay. And so when we see that in water, or we see that in the ground, something solid or a gas, it actually manifests itself differently. Okay, in each one. So talking about wave properties right here, right? When you pluck a guitar string, right, or you blow a whistle, right, the disturbance may be a single pulse, right, which is like plucking a string, or uh, or it can be that's weird. Disturbance may be a single pulse or a shock of a hammer or a shock hammer. I don't understand what that means. Shock hammer, or maybe periodic like a guitar string, right? I don't know what that means. Shock hammer. That kind of threw me for a loop there. Anyway, so there are two types of waves, right? There are two types of waves. There is a longitudinal wave and there's a transverse wave. Okay. So in a longitudinal wave, which is this diagram right here, right? In this diagram, we have particles that are displaced. So here is a spring, right? And there are two blocks on either side of the spring. And when the spring releases, it makes a wave, and the particle, right, or these boxes go in the same direction as the spring. So that's parallel, right? That's called a longitudinal wave. A transverse wave happens when the particle actually goes perpendicular to the direction of the wave, right? Perpendicular to the direction. Okay. So light, for example, light is an example of a transverse wave. Okay. So let's talk about what a wave looks like, the description of a wave, right? There are a couple different things you can look at with a wave. Here is a single wave, and when you have the distance from one peak to another peak, that's called the wavelength, right? The velocity of the wave is just how fast the wave is going, but the height between the midpoint and the peak is called the amplitude, okay? Everybody got that, right? That's pretty easy, right? Pretty easy. So your first question in this unit then is going to be, which wave description is the distance between the two peaks? The velocity, the amplitude, the wavelength, or none of the above? I just said I don't sweat, and I'm like sweating like crazy up here. Is it hot in here? Is it just me? It's probably just me. Doing a lot of talking. All right. The vast majority of you are getting that one correct. Wavelength is C. Oh, I forgot to change the things to C. But yeah, it is C. So good job right there. The distance between two peaks. Okay. So you can actually also describe a wave as a frequency as well, right? And really the frequency, right, is the number of wavelengths per time, okay? So for example, 1 hertz equals 1 cycle per second. So usually that time right there for the frequency is 1 second. Like how many times the wave goes around in 1 second, right? That's the frequency. So you can also do it by period too, where the cycles per second, right, is divided by the frequency, and then you'll get the period. So in this one here, you have the frequency is equal 1 over the time, right? However many waves you got over the time. But over here, it's 1 over the frequency instead, and then you get the period. So you can see how one is like the opposite of the other. See, this one F is on this side, frequency is this side, the time is here. But on the other side, on period, time is over here, and frequency is at the bottom, right? So that's the difference between those two things. So when you see things like 4 hertz, right, that's what that means right there, right? 4 hertz is 1/4 of a second. So to show you the difference here, right, when you have a time of 4 hertz right here, 1 over 4 seconds, right, what it means is that within 1 second, you have 4 humps, 4 peaks. Whereas if you had a period of 1/8 seconds or 8 hertz, you have 8 peaks inside of a second, right? So this is the frequency right here. The frequency is 8 hertz. So 8 peaks inside of 1 second. Whereas the period here is 1/8 second, right? And it's at the bottom. Up here, 4 peaks is 4 hertz for the frequency. And then for the period, it's 1/4 seconds. That takes us to electromagnetic waves, which is basically light, right? Consisting of vibrating electric and magnetic fields that oscillate perpendicular to each other and in the direction of wave propagation. So the thing I want you to remember about light is that there's this thing called the speed of light, and the speed of light is actually 3.0 times 8 to times 10 to the 8 meters per second. That's the speed of light, which you already probably know that because we did a calculation of that before when we were talking about how fast light travels from the sun to the earth. Remember that, right? So you should already know this number right here. You don't have to memorize it, but we're talking all about this just so we can get to this slide right here, which is the electromagnetic radiation slide, okay? So the things I want you to see here and learn from this particular slide here, right, is that when you're looking at electromagnetic radiation, and this is probably what we'll end the class on today, and we'll end the information from the exam on, right, is that the most powerful energy is actually gamma rays, right? And then it goes to X-rays, then it goes to ultraviolet, and then we have the visible light. That's a light that you can see, right? Have you ever wondered why green lights are green, right, when you're on traffic lights? The reason why is because it's right. Green is right in the middle of what you can see, and that's why it's green. That's why traffic lights are green. Then we have infrared light. Then we have microwave, and then we have radio waves, right? So each one of these things here corresponds to this kind of one of these electromagnetic radiations, right? And so the thing I want you to notice here is, of course, visible light. But then if you see over here, over at gamma rays come from like stars. You can use it to get a PET scan. But the coolest thing about gamma rays is that it's pretty small, but it makes the Hulk. The Hulk actually makes gamma rays actually makes the Hulk, right? Then you use X-rays here. Ultraviolet actually, you can use it to clean your teeth. Use it for night vision, right? But, sorry, that's infrared. Clean your teeth, but it also breaks molecules apart too, and that's why you get skin cancer, right? And then we have the visible light here, which is the colors you can see, and then we have infrared and microwave. Infrared is for the remote, and then microwave is your cell phone. Your cell phone has microwaves, right? And the wireless routers are also all microwave. And then we have radio waves, which is the radio, right? The radio stuff. So the last question for today is this question right here, and then we'll end the lecture. What type of electromagnetic radiation made the Hulk? And I expect you all to get this right. Oops. And the vast majority of you got that right. It is gamma rays. All right. That ends the lecture. If you have lab with me, stay behind. Um, Make sure you put your tables back together. And today's lab is kind of fun. So let's get ready to do today's lab.